An NMR question here that looks at the analysis of compound L from the leaves of a common garden herb. So we're told in part A that compound L contains carbon, hydrogen and oxygen only, with the following percentage composition by mass. And you'll notice that the oxygen percentage is missing. We've got a molecular ion peak at M/Z164, and we've got to show the molecular formula L is C10H12O2. It looks at the carbon-13 NMR spectrum of L. So here it is here, and we've got to say how many different carbon environments are present in the molecule. Part C looks at the proton NMR spectrum of L. So you can see we've got 3 signals. So the shift values obviously were read off the scale there. We've got the integration values, so 5H, 1H, 6H, and we've also got the splitting patterns. And this one here has been expanded, and there it is there. So we have to state why TMS is added. What information can be deduced about compound L from this integration trace? And then the main part of this question, this is worth 7 marks. We have to come up with a structure for compound L, and we must include information from parts A, B and C. So not just the proton NMR, the carbon-13 and the elemental analysis. If you want to have a go at that, pause the video and then play on and I'll go through the answers. Part A, we've got to show the molecular formula of L is C10H12O2. So you can see I've scribbled there the M/Z at 164 means that the MR of the molecule is 164. So we're going to do an empirical formula calculation. We've got the carbon and the hydrogen percentages, so the difference from 100 is the oxygen percentage. So we've got mole ratios when we divide the percentages by the MR of the atoms of 6.1 to 7.37 to 1.22. So we just divide those all by the smallest, which is obviously this one here, and we get C5H6O. Now the MR of that is 82, which is half of 164, so therefore the molecular formula is double that, C10H12O2, which is what we were asked to show. Carbon-13 NMR spectrum of L, and you can see straight away as soon as I'm looking at these spectra, I'm writing down from the data sheet what the shift values telling me about the carbon environment. So this orange one here belongs to an ester carbon. The green ones here are just regular carbon to carbons, and I haven't labelled this up yet, but these correspond to benzene carbons. So how many carbon environments have we got? We just count the peaks and you can see that there are 7 peaks. Part C deals with the proton NMR. So we've got to state why TMS is added, and that provides a reference peak, or you could say it has a shift value of 0 ppm. What information can be deduced about compound L from the integration trace? The relative number of hydrogens in each environment. And now we're going to start and work out what the structure of L is. So you can see I've gone to the carbon-13 NMR information in this little part of my answer. So I'm saying that the peak at delta 185 ppm suggests that L is an ester. And then the mark scheme, it says that you have to say this. And then you can say either of these two. Either the pink peaks that are highlighted, the ones between 120 and 150, suggest that we've got a benzene ring present, or The peaks at delta 20 to 40 suggest C double bond C. Proton Nmr, so I'm starting at the lowest ppm values, the lowest shift values. So that doublet at delta 1.2 indicates an RCH environment, and because the integration value is 6, that's telling us there are 6 protons in this environment. So we're looking at probably 2 CH3 groups, and because it's a doublet, they're going to be attached to or adjacent to a CH, a single H, and that's why we get the doublet. And obviously the 6 hydrogens give us the peak area of 6. So it looks like we've got this feature in the molecule. The peak at delta 2.7 ppm is a heptet or a septet, or you could say a multiplet of 7, and that indicates this environment, and this confirms or backs up our thoughts that it's an ester. There's only one hydrogen in this environment from the peak area, and the fact that it's a heptet is supporting that we've got 2 CH3 groups adjacent. So in other words, we can now say we've got this feature in our molecule. So this green hydrogen here is causing this delta 2.7, and it's split into a heptet because of the 6 adjacent hydrogens, and it's at 2.7 because it's an H to C to a C double bond O. So you can see there I'm just processing this information as I go. I've used up 4 carbons. Remember, there's 10 altogether in the molecule, so we've got 6 left, and we're thinking that it's benzene ring, so that could account for the 6 remaining carbons. The peak at 7.3 now indicates a benzene ring. Its area is 5, so 5 hydrogens, which would confirm or back up the fact that we could have a benzene ring attached here, and that is actually the answer. Just do a final check. Have I got C10H12O2? Yes, I have. So I'm drawing my answer into the box now. So the structure of compound L is this. That's worth 2 marks, and just wanted to show you an alternative answer which isn't quite right, but you would be credited 1 mark for this one. And basically the difference is the ester bond's the wrong way around in this one. So this is the right answer, but this would have got 1 mark.